Saurabh, I think you can start. It's 5 minutes now.
Yes, yes, we'll start at 2 minutes. Yeah. So good evening, everyone. So on behalf of organizing team of Hackathon 2026, which is organized as a part of Semicon India, I welcome you all. Good evening. This hackathon is organized by SEMI, strategic partner ISA, industry partners KLA and Applied Materials, academic partner VIT, Vellore, and implementation partner IFOSIN. So Semicon India is a premier platform that brings together the global semiconductor leaders, industries, academia, policymakers, innovators to accelerate the growth of India's semiconductor ecosystem. So today's session, we are focusing on the problem statement which is provided by KLA, that is AI-based restoration of degraded semiconductor inspection image. So today's session is important as it will provide you with an opportunity to clarify your questions, um, validate your technical approach, strengthen your solution before you submit your solutions for the phase one. Um, and we will also have a Q&A session. So this session is mainly for the Q&A where you will ask your questions. Put your questions in chat box. We will take them once we have explained you the key concepts behind the problem statement once again. And so today again, I am privileged to introduce to our expert speaker from KLA, Mr. Akshat Singh and David sir. Um, they both are part of KLA, working in the ecosystem of KLA. So mostly the mentor and the technical spoke for this problem statement is Mr. Akshat Singh, who is ML engineer at KLA, specializing in vision foundation models, self-supervised learning models. Uh, he is an IIT Madras computer engineer graduate. So he works across the complete AI model life cycle. And his experience in this particular domain will definitely help you provide valuable guidance along with our mentor also, David sir. I'd like to thank you both of you for joining along with the KLA other team members. And now I will invite you to begin the session. Over to you, Akshat.
Okay, thanks, Saurabh, for the introduction. I think for today's session, we discussed that we'll just quickly go over the problem statement once more to just sort of refresh it. It won't be as long as it was in the first webinar, but I'll just quickly go over the main points from the problem statement and then we can open the floor for questions. Second, I'll just share my screen. Okay, hopefully you can see my screen. So, hi everyone, good evening. This is a refresher on the problem statement for the Semicon AI Hackathon. The main task for the problem was image restoration. And we sort of started with the point on what is a good image, and where we discussed that a good image is something which is sharp, which is noisy, which has a lot of details, which has a lot of resolution. So if you zoom into a good image, you'll still be able to see good resolution. Uh, However, if there's a good image, there's also a bad image. A bad image is something which is very noisy, very low resolution, very few pixels. There's not a lot of signal in the image. That's what a bad image is. And usually you can go from a good image to bad image by image degradation. So a bad image can have these qualities, right? Like noise, blur, low resolution, etc. And this was again a brief overview on what noise is and there's not just a single type of noise, but in fact, there's multiple different types of noises which are present in real world images. For example, let's look at this ground truth image, right? So if I were to add some Gaussian noise to it with this distribution, um, the image will look something like this. This is a fairly low level of noise, but I can keep on going to add more and more noise to these images. And as you can see, the rightmost image is extremely noisy, and it's this Gaussian distribution which is being followed. The way to read this distribution is fairly simple, that the x-axis is noise value and the y-axis is probability density. So for this particular curve on the right extreme, we see that higher noise values like 1 and 1.5 still have high probability, while for the low noise Gaussian distribution, these higher noise values have almost zero probability, so they don't come into play. That's why the rightmost curve is the most noise. And then another type of noise is speckle noise, where again I have a similar distribution as Gaussian, but this time I'm adding speckle noise. As you can see that these two images, the one at the top which is produced by Gaussian noise and the one at the bottom which is produced by speckle noise, they do look quite different. So these are in fact different types of noise that you have to deal with in the real world scenario. One very important point to note is that Gaussian noise is additive in nature, that it gets added to the image, while speckle noise is multiplicative in nature, which means it's getting multiplied to the image. So in fact, speckle noise then depends on the intensity of the image. So other than noise, you can have blurring in your images. So here I have different strengths of blurring kernels. The strength of these kernels are increasing from left to right, and you can see that they're producing more and more blurred images, right? And that's one way of having lower information in your image. The other way is resolution, right? That you can just downsample the original image to fewer pixels. For example, if the original image was 512 cross 512, I can just sample half the number of pixels in each dimension, and I get a 256 cross 256 sized image. So here you can see from left to right, I'm downsampling it by an increasing factor from 1.5x to 4x, and you can see how a downsampled image looks like. So it's important to see how these um, image degradation models like blur, resolution, noise, how they make the image look like instead of just knowing the mathematical model. This also sorts of help give you an intuition or some sort of idea on how you can develop solutions to denoise or deal with these sort of image degradation. However, real world image degradations are much more complex. It's not just noise or just blur or just downsampling. It's usually a combination of all of these things, right? So here, let's say I have a clean image with no degradation. This is our original image. I can apply blur to it. It looks something like this. I can then add speckle noise on top of this. So the image now looks like this. And I can then further downsample the image. So it now looks like this. So you see, by following this pipeline, we've gone from the original image to this really noisy degraded image, right? And one point to note is that these image degradations, they can appear in any order. So you have to be careful about that. So following from this, what was the hackathon task, or what is the hackathon task? That we've taken a good image and we've applied an image degradation pipeline to those good images, and we have created a set of bad images, right? These bad images have been created with these three types of image degradations. So you should pay close attention to these three image degradations. The first one is speckle noise. I've shown you what speckle noise looks like in the previous slides. There's image downsampling, which is that you're sampling pixels to create a lower resolution image, and then additive Gaussian noise, right? So we have both multiplicative noise and additive noise and downsampling. However, don't read in too much into the order in which these three things are written. In the image degradation pipeline, we could have used any order to create the bad image, and you can either make your solution robust enough to deal with any order of degradation, or you can also, in fact, create models or create solutions to figure out the exact order and then try to restore the images. So the hackathon task was that you will have these set of bad images and you need to create an AI based solution to get back to the good image, right? That is the hackathon task, which is to learn this transform, right? You need to obtain clean images from degraded images. And this task is called image restoration. And this is not a trivial problem. So let's take an even closer look to it in some mathematical form, where let's say again we have a true image called X. We apply a function f on top of it to degrade it. So we now have a degraded image or a corrupt image Y. This f, in our case, like we've said, is speckle noise, downsampling, and additive Gaussian noise. And the hackathon challenge is to somehow develop an AI-based solution to get back to the true image X from the corrupt image Y. And this is not
Akshat,
a trivial problem. Sorry.
yeah, Akshat, maybe you want to pause and sometimes and ask people if they have questions and they want to answer questions. And let's
Yeah.
pause
Okay.
after every slide going
Sure. I
forward.
will pause after this slide and then we can ask questions. Yeah. So this is what the images will look like. So this is the ground truth image and this is the noisy low resolution image. And you can see the histogram here for comparison, right? And the goal is to go from noisy to ground truth. However, this is not a very easy problem because for the same noisy image, there can be multiple different realizations of the true image or the ground truth image, right? So the task is how do you find this good image? And that's the main crux of the hackathon problem. There are a few more examples of these pairs, and there are some details on the data set that which we have released, right? So now I think I'll pause at this slide like Danny said, and we can open the forum for any questions that might be there.
So if you guys have any questions, please put it in chat box. So we have a question like, should we also train our model in the frequency domain to improve image restoration performance? Or is the training only in the spectral domain sufficient?
Yeah, that's a good question. I Yeah, you can actually evaluate whether frequency domain training is helping you or not. Um, so you can either think of doing a combination of those two or just one, but that is something that you will have to evaluate. But training in frequency domain is, I mean, definitely a good idea, and think it can be like a valid direction for you to approach.
Okay. We have like how the submissions will be evaluated. Then we like, does the final evaluation contain same images?
Okay. So the final submissions will be evaluated on three different criterias. The first one is the quality of the restored images which are being produced by your solution. So we'll give you as a test set, right? Only low resolution noisy images, and we will run your solution through those images to produce denoised images, and then we'll compare those denoised images to the ground truth. And we have a metric internally which we use to track how good the restoration quality is. So that's one axis. The second axis is how efficient your solution is, how fast it is in terms of throughput. Um, And that's not just your model, but it's the end-to-end pipeline from reading images from the disk, running your model on the GPU, and then storing the restored images back to the disk. And the third axis of evaluation is how good is your training hygiene, your compute hygiene, whether you're following the best practices recommended in machine learning and deep learning space. So the the final participant solutions will be ranked along these three axes to determine the finalists. And does the final evaluation contain SEM images? Um, so the final evaluation might contain some images. The final evaluation will be done on a test set which is held out. It's so some images will be in domain, which means you'll see similar images in the training set. Some images will be out of domain, which means you won't see images similar to those in the training set. So you have to make sure your model generalizes to both these types of images.
Okay. So what kind of images will be provided? Is that we have already answered. Again, we have a question like, do we have to mainly focus on 3 degradation and noise mentioned today, or are there any
Yeah,
other
it's only
types
those
here?
three. Yes.
And during the evaluation phase, like, will the benchmark consist of individual degraded images proceed by one, or will the model be tested on batches of multiple degraded images simultaneously?
Mm, okay, it will mostly be tested on batches. And one point to note here is that as part of the final submissions, you will be required to submit a script which loads these images, runs it through your model, and then stores the images. So, I mean, it's up to your script then whether you will process it one by one or whether you'll do batch processing. It's obviously preferred to do batch processing, but sometimes maybe someone has created a very large model that they're not able to fit batches in on the GPUs. In that case, it'll be processed one by one, but in most cases, I think it'll be batch processing.
Mhm. Okay, so we have also collected few questions. So we have one question, three questions, like attached to each other. So are participants allowed to use publicly available external dataset? Because we already have given the dataset, made the dataset available. So that is one thing. So before, like, fine tuning on the official KLA dataset that you will be giving them during the test phase.
Okay.
So
Yeah, I think I'll answer all three of those questions together. So, yeah, the participants are allowed to use publicly available external datasets for pre-training or for domain adaptation. Um, they are free to use any dataset which is publicly available under a permissive license, which means under the license, you should be allowed to use it for the competition task or for learning, etc. Um, the same thing holds for publicly available pre-trained model weights. You're free to use pre-trained model weights, and you're free to initialize the models with that and fine tune on top of it. Um, Having said that, in your final report and the final submission which you are making, this can be a document, a PowerPoint, or your train code itself. We would like that you include all the details of the public data sets which you have used. This will include their name, their links, their license, and the research paper where you got it from. Same thing about the models which you're using. If you're using publicly available models from platforms like Hugging Face, PyTorch, TensorFlow, etc., it's okay to just point us to a link to that particular model card or the dataset card. But again, at a high level, you're free to use any publicly available model weights, dataset, model architecture, etc. Okay, then there is a question, would you recommend optimizing mainly for PSNR or for perceptual quality? Um, so the recommendation, as a recommendation, we have given three different metrics. The first one is PSNR, the second one is LPIPS, and the third one is SSIM. And so we don't want to give you any bias on which metric to target. And I think this is also representative of how you'll solve these problems in the real world, where um, you won't figuring out the metric to optimize is part of the problem statement itself. So, I mean, you're free to use any of those metrics or even some other new metric which you discover while reading through this problem statement, or you're free to use a combination of these, and that decision is finally up to you. Then, is it mandatory for the model to detect the sequence of the different noises mentioned today? So it's not mandatory for the model to detect the sequence. In fact, it's perfectly okay that your AI model does the denoising in like a single shot. It doesn't need to figure out the sequence. But sometimes figuring out a sequence or spending time to figure out the sequence might be helpful in some cases, where you can then push in those priors into your model development, and that can help the denoising process. But it's not mandatory. Um, Then NVIDIA H100 is paid, and the last time we said it will be evaluated on NVIDIA H100. Yeah, so the evaluation will be done on our side. I think it's okay. If from your end we just need a script that you can make sure will run on an NVIDIA GPU and will perform inference. So that's all that's I think that's required from the participants end. When benchmarking inference time, does the timing include pre-processing and post-processing, or only neural network forward pass time? Yeah, during benchmarking of the inference time, the timing is not only neural network forward pass time. It's in fact end-to-end runtime of your script. So this means loading the images from the disk, um, pre-processing, pushing the images to the GPU for execution, model forward pass, and then storing the images back to the disk. So you should think of optimizing your entire inference pipeline end to end instead of just the model. Will the hidden test dataset contain degradation patterns or noise levels different from the provided training dataset, so that we should focus on building a model that generalizes well? Okay. So the hidden test set will not contain degradation patterns which you have not seen in the train set. The noise levels may be slightly different, but it won't be very drastically different that a model that you train on those noise levels, it won't work here. However, the image content itself or the type of images might vary a lot. For example, instead of natural images in the hidden test set, you might see a lot of manufacturing images or industry images or city images, etc. Right? So that's the main difference. Would you recommend adding a dedicated defect aware loss, or would our existing pixel structural and frequency based losses already provide sufficient supervision for preserving them? Uh, Good question. So the data set that which we have given as part of the hackathon, there's no defect as such in the image. So for now, you don't need to worry about it being defect aware. Um, so since there are no defects, you're fine to use the losses which you have mentioned in your question. For the degradation types in the benchmark, should we specifically prioritize Gaussian noise, speckle, and downsampling during training, or should we give equal importance to the other degradation types as well? Um, so for this hackathon task, there's only three types of image degradation that you need to worry about. you don't need to worry about the other degradations. So the three types are Gaussian noise, spectral noise, and downsampling. Um, do we have to design batch processing or one by one? Um, I think it's preferred that if you do batch processing in your inference script, because that will be much faster to run on GPUs rather than one by one processing.
Okay, we don't see any more questions as of now. Maybe we can proceed if you have any further slides in.
Okay. Yeah, I don't have any other slides apart from what I already showed. Um, yeah, I think that was already my final slide, so it's okay.
Mhm. Okay. Okay, if anyone has any further questions, you can put it in chat box or just raise your hand if you want to ask the question.
Okay, I see some more questions. So for loss, I was using BCE. Is there any need to train with MSE or others? Okay. Yeah, I think as part of the problem statement, you should definitely explore other losses which are more task specific, and those losses will definitely help improve the performance of your model. So which pre-trained models have previous successful teams used? Are there common mistakes teams make on PS1? Is inference speed often the deciding factor? Okay. So which pre-trained models have previous successful teams used? We are deliberately not uh revealing that, because that's the problem statement and it's on you to figure it out. Which models do you think will work best? Um, is inference speed often the deciding factor? So inference speed is definitely one of the important factors to consider, because so all of the three factors which I mentioned are given sufficient weightage in the final scoring, and any of those factors can be important for deciding the finalists. Are there recommendations for balancing restoration quality and out of distribution robustness? Um so I think our recommendation would be for balancing restoration quality and out of distribution is maybe you can focus some effort around different image augmentations. So, and these augmentations can be noise addition from the pipeline, which we have already shown. They can be other noises as well, other different augmentations which are used in regular model training. You can also think about using those. So I think that would be my main recommendation for you to think about restoration quality and out of distribution. The others would be exploring different losses or different objectives which people have published about or used for this particular task. Okay. For how many batches do we have to design? Um, yeah, I think it's okay. You can, whatever you think is like a good trade-off between speed up and what can fit in the GPU memory. Yeah, you're free to use that batch size in your processing. Since the benchmark contains only Gaussian noise, spectral noise, and downsampling, is the test primarily evaluating how well the model handles these three known degradation mechanisms, or is generalization to unseen combinations and severity levels also an important part of the evaluation? So the evaluation will evaluate only on these three known degradation mechanisms. However, the severity level is in fact not the same for the train images as well, right? It's been sampled from a range. It's not the same exact noise applied to all the images. It's sampled, right? So within the test set as well, the noise has been sampled from a similar distribution. But you don't have to generalize to unseen severity levels or unseen combinations. That's not part of the problem statement.
Okay, yeah, Pradnya, yeah, you can ask your question. Yeah. Yeah, we have a question in chat box.
Okay. Mm, okay. So I think there's some questions around compute. So for compute, I think we have recommended that you should consider using the free GPUs which are available on different platforms like Google Colab and Kaggle. And I mean, we have found that participants are able to get a good solution uh, ready even with this amount of compute, because the data set which we have created, it's not extremely large. It's not like millions or billions of images that you'll need a lot of compute to really crack this problem. So we have, I mean, considered this point while creating the data set. Um, for PS01, is the hidden test ranking based on a fixed weighted combination of these metrics, or are these reported separately? And does the benchmark apply any output range clipping or normalization before scoring? Good question. So we have a fixed weighted combination of these metrics. Uh, the exact weightage is not being revealed as part of the problem statement, but yeah, you can, these are not reported separately, but like a fixed weighted sum. And we will not be doing any clipping or any normalization of images before scoring. We will directly use whatever images your solution produces for scoring. So make sure any clipping or any normalization which you want to do, you should do as part of your model or as part of the post-processing step in your solution. We can implement CUDA specific code in our design to process faster and load data. Yeah, you are free to do that. Since you know it will be running on an NVIDIA GPU on our end, you are free to use any CUDA specific optimization which comes to your mind. Would you recommend that teams explicitly optimize their architecture for these three degradation mechanisms, or is the expectation that a general restoration architecture should handle them without degradation specific specialization? Uh, there's no such expectation from our end whether your model architecture should be degradation specific or very generalized. It's a design choice which you will have to make. We are not making any expectation around that. However, since you know the problem statement and you know the degradation mechanism, if you can get better accuracy and better performance by making your architecture degradation specific, that is definitely a good idea to explore.
Okay. A few common questions, like what common mistakes should participant avoid while training and evaluating their models?
Okay. Um, so one thing I'll suggest is, which I often see people missing, uh, is make sure you actually look at the images which your model is producing instead of just looking at the metric, right? Because the metric or any weighted combination of the metric which you can use I mean, they give you a good aggregate overview of what's going on in the training data set, in the validation data set. But sometimes people miss just looking at the images and seeing what's happening, because once you look at the images, you know that, oh, my model is probably missing speckle noise, it's probably missing Gaussian noise, and maybe I can optimize my architecture or loss so it's more robust to that. So that's one suggestion. The other would be that you should make sure you follow all the standard well-defined practices of machine learning and deep learning. Uh, Make sure you use transfer learning, good model optimization, weight initialization, etc. So as long as you're following these good hygiene practices, I think it should be okay. And the other thing would be, which is a direction which remains a bit unexplored, is image augmentation to improve the generalization of your model and increase your data set as well, right? Those are like my main suggestions.
Okay.
Akshat, is there something we can tell the students who have not done a hackathon before, how to get basically started with a hackathon and how to build these things in a
Oh,
structured way?
okay. Um, okay. So what so for anyone who has not done a hackathon before, I'd suggest you download the data set and just go through the images once. Um, since you'll be developing AI-based solutions, I'll say that first get your data pipeline ready. This is the Python code that will read these images from the disk and load them and pass it on to your model. Have like a very basic model, like extremely simple CNN that you can put in, or extremely simple transformer that you can have, and then use like a very basic loss. So essentially, a very basic pipeline, um, from data loading to the model to the loss. You should try to get this ready, and you should try to make sure that this is running correctly, right? And a good way to make sure of that is just reduce the size of your data set. Just take one or two images and run it through your model and try to train it. Your model should ideally overfit on these images. And if you see this overfitting happening, since you're only training on one or two images, right? So that's like a good sign that there's no extremely obvious bug in your pipeline. So once you have that setup ready, you can start to think how to optimize each of these individual components separately. You can think whether you want to add some input pre-processing to your images, right? This can include normalization, augmentation. The next optimization is on the model side, whether you want to change the architecture, increase the size of your model, add some degradation specific architecture to your model. That was one of the questions. The next step in the pipeline is the loss. Maybe you explore different losses which people have used for this task and see how your model's performance improves or degrades for each of those losses. And then the main part comes about, you really will need to track your experiments, right? Otherwise, it will just become a jumble of things. So maybe having some sort of documentation on different experiments you are doing and what is helping versus what is not will also be very useful to do. Okay. Mm, I think there's some questions in the chat. Is there any benefit in training with additional synthetic degradation types for robustness, or could that actually hurt performance on the official benchmark? Yeah, good question. Um, Again, I think it's a bit difficult to say this because, I mean, the models are so large and the data is so huge. I don't want to make any claim around this, but um, you, I think what you should do is you should test this out on your own held out test data set and see whether this helps improve performance. Um, so there's both angles to this argument. The first angle is that your model has limited capacity, and you you know what sort of degradation for it to focus on, and if you make it focus on others, it might actually hurt performance, but on the other hand it can help in robustness as well. um so yeah, I mean, what I'll suggest is this is something for you to test and evaluate on your own held out test data set, and then make the call whether this is helping or not. Do you have reproducibility requirements, fixed seeds, environment specs, deterministic ops beyond just saving checkpoints and configs? Yes, we have reproducibility requirements. You will be asked to submit a train script using which we should be able to reproduce your trained checkpoint weights. And this, even for your inference script, it's recommended that you, along with the script, you submit an environment spec. So we should be able to run your script, right? For the OOD test set, is the distribution shift mainly from different semiconductor structure sources, or can the degradation characteristics themselves also change, for example, different noise strengths or noise distributions? Yeah. So for the out of distribution test set, it's mainly coming from different types of images from different sources and having different structures. It's not different noise characteristics or different noise strengths. When the restored image is zoomed in, will the preservation of fine structural details be considered during evaluation? No, the final evaluation will only be on the full resolution image. Okay. What is the most common failure mode you've observed in baseline restoration models? Noise removal, fine detail reconstruction, hallucinated structures, or generalization to OOD images. Um, Again, this, it's a bit difficult to make a general statement because different solutions and different models have different failure modes. And I think you've listed very well most of the common failure modes which these models have. I've seen different models have different failure modes. It's difficult to say which one is the most common. It mostly depends on the training pipeline and the model that the participants have decided to use.
We have few more questions, Nick.
Yeah. Okay. What inference time would you consider favorable or competitive for the final model on the benchmark hardware? Is a target latency? Okay, so we don't have a target latency or approximate range for the inference time. It depends on the model that you have developed. If for the model that you have developed, if you show that you have optimized it a lot, even that is good. However, um, like having a smaller model getting a good sensitivity performance, that is always like the preferred case. Since the evaluation is based on hidden weighted combination, are there any loss functions or training strategies that generally align better with these evaluation metrics, or is that intentionally left for participants? Uh, yeah, that is, yeah, the loss function choice is not imposed on the participants, and it's part of the problem statement to figure what loss is working best. I mean, common losses which people just start with are MSE, L1 loss. People also use SSIM as a loss as well. Are we allowed to use provided ground truth images to generate additional synthetic degraded training pairs using our own degradation pipeline? And can we also use publicly available semiconductor image dataset or pre-trained restoration models? Yeah, you are free to generate additional synthetic images from the training pairs and from the ground truth images. And you're free to use any publicly available, not only semiconductor, you're free to use any publicly available image-based dataset and pre-trained restoration models. Given that the license for those datasets, the models allow you to use those in this particular setting.
Okay. One more common question, like what information you may basically want from the participants, like clearly mentioned in the say for example the PPT they want to submit and GitHub repository. So this again we already mentioned, but a clarity on that.
Oh, so the first thing we will want is an inference script, like I have said, which loads the input images, performs inference on your trained model, and stores the images back to disk. Right? That's the number one thing. Your script should accept the input directory as an argument and an output directory as two arguments. Those are the two main things. The Along with the inference script, what should ideally come packaged is a set of dependencies. If you have some extra dependencies which you want us to use while running your script, this is like uh, generally how you will distribute a Python script. You are expected to distribute it to us. Second is the training code, how you have trained your model, how and your training should be reproducible. So, and we'll check if you're following standard DL training practices there or not, whether you have good training hygiene there. Again, a set of dependencies to run your train script will be extremely useful. The third one will be like a document. This can be documentation in any format, right? This can be a PowerPoint file or a Word document or anything which explains your solution, explains your understanding of the problem statement, how you have approached the solution, what is the solution which you have developed, and if you have used any public data sets, any public models, you should add details on those. What is your training pipeline? What is your inference pipeline? What optimizations have you made? And in the same document, instead of just writing what worked well, you are also free to add details on the different things which you tried and what results you saw with those things. Why do you think they didn't work out well, and why you went with your final solutions? So, and yeah, I think those three are really the main things which we'll want.
Okay. Regarding the document that you mentioned, so we will recommend them using the PPT Power presentation, which we have already given them as a ideal template which they can use, where they have to explain what they have understood, uh, what they're trying to solve, technology they want to use, what all the points that you have mentioned,
Yeah.
that's already
Okay.
present on the landing page. So
Okay.
yeah,
Nice.
yes, yeah, thank you for that. Like few questions, two more questions, and then we can maybe wrap up.
If an image is large and we use tiling internally, is the total time for processing all the tiles counted as the model's inference time? Yes, it will be counted as the total for all the tiles since that's the time for processing an image. However, the images in the test set won't be too large. They'll be like 256 cross 256 or 512 cross 512. If we aim for a particular inference time target, what would you consider the best balance between restoration quality and latency for this challenge? Mm, yeah, I think, okay. So the primary thing is uh, restoration quality, and latency is equally important, latency or throughput. However, what is ideally best is a smaller model with low latency, but I mean, obviously you can't always have that. So what I think you should aim for is to get like the smallest model or the fastest model with the highest latency target that you can achieve. And there's like different ways to get to this, right? You can try larger models, and at some point you'll see that the larger capacity is not really helping performance. And that's really the point where you know that you've hit the largest size that you can go to. And then you can try different techniques like regularization, augmentation to sort of try to reduce down the size of your model. I mean, that would be my main suggestion on how to really tackle this.
Okay. So I hope we are done with the questions. If any further questions we have, you can pin us on email or WhatsApp. So email we have given support@ifoc.in. We'll put it in chat box also. And so right now we have more than 2,000 teams who have registered for the hackathon. So the competition is quite good. So we request every participant to give the good solutions, required solutions as per the problem statement mentioned. All details are given on the landing page. Every description, background of the problem statement, data set is made available as mentioned. And if you have any further questions, you can put it as to mail or on WhatsApp. If we don't have any further questions, we like to conclude the session. So I sincerely thank you, Akshat, and the KLA team for answering all the questions that participants have and supporting this hackathon. And giving knowledge, transferring the knowledge to participants, which they usually don't get when they are studying during their course or in the college. So all the to all the participants, please use the insights which we have shared over the this knowledge series from last session to today's session. Use this insights given and try to improve your solution and give better solution to the problem statement provided. The registration and submission date. So deadline date is 16th of August. That is for the phase 1. So please do not wait until the last day. Try to submit as early as possible so you get some time to uh, maybe do some edits in your solution if you want to. Because after the last date, your solutions will be freezed. You will not be able to do any edits on the portal. And all the session recordings are made available on the landing page. After this session is done, this also will be made available on the landing page. So do visit the landing page and will also the recordings will be mailed you through official channels. Okay. Yeah. And again, on the behalf of all the organizing team, SEMI, ISA, KLA, Applied Materials, VIT, and IFOC, I thank you everyone for joining today's session. Yeah. Have a great evening.
Bye.
Thank you.
Thank you, guys.
Bye.
Thank you,
Thank
David,
you.
sir.
Thank
you.
you.
Bye.
Bye bye.